All right, as usual, if you're not hearing me properly, yell, raise your hand, do something to attract my attention. Okay, and I'll stop and answer any queries and so on. Just some house announcements. Of course, tomorrow morning we'll have tutorial 2 or afternoon, I should say. We'll have tutorial 2 on this for ECNG2011. Okay, so let us head out now. So today we're going to start looking at the Fourier transform. Right, that's really the topic here. But in order to do that, we have to start looking a little bit at the Fourier series. Now, I know you spent several weeks doing this in the math class ECNG 2013. So I'm not going to, this is not a class on Fourier series, and I'm not going to what shall I say, go over the material that was done by Dr. Adams on this, on how to find the Fourier series of a variety of periodic functions and so on. Rather, we need to understand what my purpose, or our purpose here, is to understand, okay, that the Fourier series arose because of some things, and then we use that now to develop something called a Fourier transform, which is a relative of the Laplace transform that can be used in certain conditions and certain situations, and we will explore that. All right, so let's get cracking here. So if you were to look at this vehicle, right, you have a little toy vehicle here in a garage. And if you look at it as it is right now, you would assume that the shape of the roof is a sort of convex, a fairly conventional sort of roof. It has a curve to it, and you have 4 pillars holding it up. Yet, if you change perspective, you realize that the roof is in fact not a convex roof, but according to what you're seeing here, it's a sort of corrugated. It's looking like two normal house roofs. I think they call it a gable roof. Two sort of it's like a zigzag. Okay, and then if you shift it around from another perspective, you now see that on top of that, now there's a difference between one side of the roof and the other in terms of the length and span of it and so on. The whole point about this is that is this comment here, that perspective makes a difference. And when you it's pretty much the same thing when you're dealing with signals and systems. Depending on how you look at it and what you look at, things may change, all right? Or you get more information about it. So for instance, just looking at this thing, the only thing that I could have gathered from this was that the roof had 4 sections and that it was a curve, a convex. But as you looked at it from different angles, you got more information to add to what you knew. First off, it's not convex, and then secondly, the sections are different shapes and so on. Right? There are still 4 sections, yes. So part was correct, but you got more insight as you looked at it. So when you start to look at back now to signals and systems, if I were to give you something looking like this, right? It's a signal amplitude versus time. And some of this, of course, what I'm doing here, I'm sure you covered in the math course, but it's just to get the conceptual understanding behind it. If I were to ask you what is the frequency of the signal, then what you would do once you have the axes and so on properly labeled, you measure the duration of a period, and 1 over the period is, of course, the frequency. Right? So if you were to do this, you would get the frequency of this is some value. If I were to draw now notice that this is signal amplitude versus time. If instead I were to ask you to draw something, a graph of the signal frequency versus amplitude, what would that look like? right? So I'm asking you now, instead of amplitude versus time, to draw a graph of frequency versus amplitude, right? So instead of the time axis here, you're going to have a frequency amplitude. How many frequencies does this particular signal have? Anybody, quickly?
One frequency.
One frequency. So if I were to ask you to draw signal frequency versus amplitude, what you're going to have is something with one mark on it, representing that single frequency, which is this. So that frequency, signal frequency versus amplitude, if you look at the original thing, we know that the amplitude, right, the amplitude of this is 1. Let's assume 1, whatever it is, 1 unit. The frequency is 1 over the period, which in this case is 0.15. Sorry, the period here is about 6 point something seconds. So the frequency is about 1 over that, which is about 0.15 hertz. So this graph of signal frequency versus amplitude, you draw the horizontal is frequency and the amplitude of that particular frequency. So hold that there for a little while. If I now have cosine 3 omega t, where omega is the frequency of our original signal, obviously that signal now is going to vary faster in time. So the amplitude versus time is going to oscillate quicker, up, down, and so on. So at that point, now if I were to ask you, what is the frequency of it? It's 3 times 0.15, which is 0.45 hertz. So the line, the original frequency line was somewhere about, let's say about here, 0.15 hertz. And now it moves to 3f, which is 0.45 hertz. And then if I were to add the two of them, if I were to take the cosine omega t and add the thing, and now ask you the question, what is the frequency? What is the frequency of that? If you didn't know anything before, and this I started the class and asked you all, what is the frequency of that signal? What you would look at is to see where the signal seems to repeat itself. So from this, what almost everybody would have done is to look and see, okay, the signal starts here, it goes so, ends here, and period. So this is looking at the period. So you would have, from this, what you would have most likely obtained was that the frequency was a 0.15 hertz. All right? Yet we know internally that this signal is actually made up of a 0.15 added to a 0.45 hertz. So just the point here is that looking at this alone is not giving me the full picture. I could get some information from it in that I could watch that and say, yes, that is periodic, which is great. I could get some information from it looking at it and saying, okay, the period of the signal may be 0.15 hertz. But other than that, there's some missing information there that I can't deduce just from looking at that. However, if I were to give you this and tell you this was a frequency of 2 sinusoids, right? One at 0.45 and one at 0.15 hertz, then you now have the idea that these two signals are, so this is the original one, and this one is one that is going at 3 times that frequency. So you're getting more information and you're also getting the amplitudes here. So in other words, both of these now, both this information, the time versus amplitude and the frequency versus amplitude are looking at the same data, which is that signal, but you're getting more information from another point of view than you would have just by looking at the time signature of the signal alone. Everybody with me? Makes sense, right?
Yes, sir.
And if we keep adding sinusoids of varying amplitude, which are multiples of the original signal frequency, in other words, like I add 1 plus 3 times plus 5 times and so on, it starts to add up and you get something looking like this. And in fact, if you keep adding up enough, then this slowly evolves into something looking like a square wave. And we will see that a little bit later on, right? This little peak here will just keep getting higher and higher until you get a very sharp line at each at each transition, when it goes here, goes here, goes here, and so on. All right. So as you keep adding it up, you get multiples. You keep getting more and more. This now was actually discovered by this person that you met a little while ago in another course, which was Joseph Fourier. He was a mathematician, and he was the one that came up with this startling thing that any periodic signal, right? In other words, a signal that repeated itself identically in time, and that is the important thing, right? The signal must repeat itself identically over some interval of time, that any signal like that could be represented as a sum of sinusoids, right? Meaning sines and cosines. And you remember, a sine and a cosine is basically the same signal, it's just that they offset. There's a phase difference of 90 degrees or pi over 2 radians between the two of them, but it's the same signal, essentially. It took years afterwards to prove it, but he deduced this from a theoretical point of view by doing exactly what we have here. So he's kept adding sinusoids, and he saw that, wait a minute, if I add enough of this thing, if I keep drawing and plotting, this thing is starting to look like a square wave. And then instead of adding, so this would have been f plus 3f plus 5f plus the odd ones. He also tried f plus 2f plus 4f. In fact, forget this one, 0, dc plus 2f plus 4f plus 6f, and he got something else. And then he started to experiment with plus and minus signs and so on. So f plus 2f plus 3f, etc. Then stick in some minus sign, minus, plus, minus, do all kind of things like that. And over a long period of time, created a whole series of signals just by adding sines and cosines. And that is the basis of his conjecture and his theory. And it took a long time mathematically to prove it. But we now know this is what we call the Fourier series. We named it after a representation of a signal. And just as a side thing, as a little side swipe, he was the first person to sort of figure out this, the behavior of the greenhouse effect, right? And what the greenhouse effect was, in fact, how it worked in the atmosphere and so on. Okay, so he not only helps us with this Fourier series, he also helps us with the with our current environmental issues and so on. He sort of drew it to our attention early on. So putting it mathematically, the Fourier series is that, and you know this from the other class. Bear in mind that some of the symbols may look a little bit different, and I'm not asking you to forget what was done with Dr. Adams. I'm using some symbols here, right? Most of them will resemble. The form may look a little bit differently, but for her class, use whatever you were taught there. I'm not going to undo whatever was done there, because the mathematical structure or the mathematical approach to this is a little bit different than what we do here. So the Fourier series in sort of 3 points is that given a continuous time signal with a period of some 2 pi over omega naught, it must be periodic, where omega 0 is called the fundamental frequency. You can now represent that signal in this form as a sum of sinusoid, as a DC, something here which is a constant or a DC value, and then a sum of sinusoids, cosines and sines. All right, forever they will die out eventually. The sines get very small. The amplitudes, which are these coefficients here, right? They get small and small and smaller and smaller as you go along for certain signals, and eventually will die off. So sometimes by the time you reach k equal to 4 or 5, you would probably have nothing left. There would be no cosine or sine term and so on. Right? And this now is this particular version is what we call the trigonometric representation of the Fourier series, because you actually are formally defining it in terms of cosine and sine. And this is what you all met. And there was a formula for calculating A0, and there's a formula for calculating the coefficients of the cosines, which is the A sub k, and the coefficients of the sines, which are the B sub k's. Right? And again, in terms of the terminology, A0 is what we call the DC or zero frequency value of the signal. Remember, signals can have a DC component. DC is just a positive or a negative value that doesn't change with time. So a signal may or may not have a DC value. So for instance, our normal sine here doesn't have a DC value, but if you were to have something looking like this, this is the same sinusoid here, but it has a DC value of some amount plus the other components in here. So signals may or may not have DC values. And then the other parts of the signals are a set of weighted sines and cosines, right? And the AKs and the BKs represents the respective amplitudes of the sines and cosines. Okay, which is this is everything that you should have covered in ECNG 2013. So everybody with me so far? Anything unusual? Am I saying anything that you haven't heard before or sounding differently? Let me know. We all right? Yeah, no? Okay. So the initial frequency, or the omega 0, is what we call the fundamental frequency. And then the multiples of that are what we call the harmonics. So 2 omega 0 is the second harmonic, 3 omega 0 is the third harmonic, and so on. All right, the first is the fundamental. Some people, like musicians, for instance, sometimes call this the first harmonic. Instead of the fundamental, we'll call this the first harmonic, right? Right, so those of you who play musical instruments will probably know it like that. And each sine and cosine term represents a single frequency. So when you put all those things together, you get something that we call in engineering, and you would have met it in physics, something called a spectrum of a signal. You would have met spectrum already or the concept of a spectrum when you did light. When you pass white light through a block of glass, it breaks up into a series of colors, and visibly you see a number of them, and we call that the spectrum. Same thing here. If you take a signal and you sit down and you do the Fourier series on it, each of this collection of other signals, the omega 0s, the 2 and the 3 and so on, together we call it a spectrum. So like this, the one where we started the class, that particular odd-looking signal on the left-hand side had 2 components in it. So this is the spectrum of the signal. So you have the time-based signal here, and you have the spectrum here. Notice both of them are giving you information, the same information, just looking at it from a different point of view. And in fact, in one case, you get more information than the other. This one is telling you something about how the signal amplitude, you're looking at it and you're getting an idea that the signal amplitude is fluctuating. It is going, there's a peak to peak of looking like about from a peak to peak of almost 4 volts here. And in between, there's another sort of peak to peak here of about 1 volt and so on. So you're getting some idea about it, and you could look for inconsistencies. This now is telling you that that signal has 2 components, but it's not telling you much about the fact that these 2 components at some point in time are adding to give you a peak to peak of 4 volts, and at other times a peak to peak of 1. So both of them are giving you information about the signal. Together, you have a complete picture. And this would be similar to, for instance, if you go by the doctor and they hook up a heart monitor to you. When they look at the heart monitor will give you a waveform. And what they're looking at now in the waveform is sort of the shapes of the peaks. Let's say this was your heart. They're looking at the sort of shapes of the peaks and so on. But then on the other side now of the heart monitor, there's a display that from that is telling you what the heartbeat is and is looking for other irregularities in the heartbeat. So the picture itself is giving you one set of information that is useful, but the spectrum side is also giving you another set of very, very useful information as well. So you need both, okay? Now, in terms of you spent a couple of weeks doing the Fourier series and how to calculate and derive the Fourier series for a whole bunch of periodic signals, triangle waves, square waves, all those kind of things, right? And that is all right, and is still there. We're not going to do that. I'm not going to ask you to repeat that sort of thing here. You have done that, and that is part of the math course itself. What you need to understand now, we need to go forward because I'm taking this now and we are migrating forward into another sort of form of the Fourier series that leads us from our point of view to something that is even more useful. You remember that there's a relationship, and we covered this before, between cosine and the complex exponential. So cosine is e to the jx plus e to the minus jx over 2, and sine similarly is e to the jx minus e to the minus jx over 2j. So what you can do is that we can substitute the sine and cosine in the standard form, right? In the standard trigonometric form of the Fourier series. We can substitute for sine and cosine in terms of e to the j k omega 0 t. And when we do that, we get a form of the Fourier series that looks like this. So xt, which is the periodic signal, can be expressed as a some coefficients e to the j k omega naught t. This is what we call the complex exponential form, or something called the analysis equation of the Fourier series. Right, so we've notice that the original form had you summing from k equal to 1 to infinity something plus another k equal 1 to infinity. You had the sines and the cosines, right? We've combined the sine and cosine using this relationship here. And when you do that, you get this version of the Fourier series being created. All right? Everybody following so far? I don't know if you came across this. Did you cover this in 2013?
Yes, sir.
Right. So once you have that, you have the complex exponential form, and notice that k goes from minus infinity to infinity. This is not implying negative frequencies. This is just because we're dealing with complex numbers. When we move from the real form of the Fourier series, where it's k going from 1 to infinity in both cases, in this case, the complex conjugates, because k is negative, the complex conjugates will cancel out and you will get back the real numbers at the end. But we need this because we're dealing with complex numbers. Okay? So it's just a mathematical artifact of the complex numbers. So again, the relationship between the two forms, you have both forms here. And of course, the coefficients are related. The AKs and the BKs are related to C by this form. The two small equations down at the bottom here. And again, in the complex exponential form, k equal to 0 is still the first is the DC or the zero frequency harmonic. k equal to plus or 1 is a first, k equal plus or minus 2 is a second, and so we go on. Okay. Now, in the Fourier, in this particular form, this is the Fourier series. This is the complex exponential form here. And the coefficients now, the CKs, are given by that expression. So to get the CKs, you take xk multiplied by e to the minus jk omega naught t, and you integrate it over the period of the signal. Notice that CK looks very much like the Laplace transform. Remember, the Laplace transform is xt e to the minus st dt. So the form of this is almost the same, and again, is almost like if I were to replace s with minus jk omega naught, I basically have the same integral inside of here. So doing the calculus for this and doing the calculus for this is almost the same, right? And this is what we want. That is going to help us now to move from from what we're doing here now into something called a Fourier transform. And again, just in terms of what we have, the one with xt tells us what frequencies are present. So when you take a signal and you run the Fourier series from it, this now is analyzing the signal or telling you what frequencies are there. The synthesis equation now tells us how much of each frequency is there. So this is kind of like a recipe, right? So this is the recipe. This is for something that you're cooking. This is telling you what ingredients. So you need this, 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 this. So that's the analysis equation. The analysis equation is taking the signal, the recipe, and telling you what ingredients are there. The synthesis equation now tells us that you need a tablespoon of that, a teaspoon of this, a pot spoon of that, and so you're going on. All right? So one tells us what is present, the other one tells us the actual weight of it. Okay? With me? Yeah, no?
Yes, sir.
Might have met it, right? So for any continuous periodic signal, and we're going back to this now, the Fourier series can determine the harmonics which make it up, that's the amplitude, which are given by the CK values, and the frequencies, which are multiples of the fundamental, and that is the spectrum of the signal. So if you take xt, and you, for each of the values of k, you work out what CK is. So you'll have C naught, C1, technically C plus or minus 1, C plus or minus 2. You could plot that now. So the magnitude of that would give you, that's a DC component, that's a first harmonic. Well, of course, because it will be plus or minus 1, you will actually have a negative here. The second harmonic, and remember, this is just complex conjugates, you're only working, so this is 0 hertz here. This is omega naught. Sorry, this is 0, this is omega naught. It's 2 omega naught, let's say 3 omega naught, and so on. So if you only look at the real frequencies, you actually have what the spectrum of the signal looks like. So this is, in fact, a plot of CK gives you the spectrum of the signal. All right? So let's just look at a simple example that we could use this as is before we move on. If I were to give you something looking like this, so this is a square, well, not a square wave, this is a rectangular wave, right? It has some duty cycle. Remember, the duty cycle is how much it is on, right? On over, off, on over total time, right? So this one is on for a particular period of time, and this is the overall period here. So if I ask you what is the DC level of that signal, right? The DC level, remember the coefficients are given by the synthesis equation, which is the CK values, in other words. And if you forget what that looks like, remember the Laplace transform. So once you could remember the Laplace transform xt e to the minus st dt. If you remember this, and in your mind, don't do this on paper because that is not the relationship, but if you remember this and you say, okay, if I substitute x for minus jk omega naught into here, then I get the synthesis equation here. And then I'm integrating over the period of the signal. Okay? So you could always remember it as this is why I told you early on that if you know the Laplace transform, we could use that very easily to recall some other things and develop some other things with the Fourier. So what is the DC level? The DC level will be the C0, k equal to 0. So if C0 is first off, C0 will be 1 over that. You remember you have a e to the minus jk omega naught t, right? Omega naught is 0, so this whole thing is 1. So you're basically integrating xt between t1 and minus t1, and then you're averaging it over the entire period of the particular pulse. Okay, if you do that, you get that C0 is 2t1 over t. Remember, this is the DC component here. So 2t1, which is this length here, 2t1, this is 2t1, and this is t here. So C0, which is a DC component, is simply 2t1 over t. And from that, you could instinctively sort of see something. The smaller the duty cycle, in other words, the smaller this time is, or the smaller the signal is on, the lower the DC value would be. And the bigger this is, or the duty cycle, the bigger that is, the higher the DC value would be. And in fact, if you were to make this signal all the way to t, it means that this signal will just be a straight line at amplitude 1. And that makes sense because if this is equal to that, the DC value would of course be 1, while the amplitude here is 1. So it will be 1, let's say 1 volt, if that's a voltage signal. All right. So for a rectangular signal, by varying the duty cycle, you can vary the DC level. And in fact, this is used extensively in electronics, in communications, to do something called pulse width modulation. Okay, where you vary the width and you use the DC level as a sort of signaling tool, right? So if it is a 50% duty cycle, meaning that the wave is on half of the time, instinctively you would see that if this is half of that, the DC value should be around half. But it's very easy to figure out. We just saw that C0 is 2t1 over t. And if 2t1 is half of t, just substitute inside of here and you're going to get that C0 is a half. So I could vary this. You would see in some of the past paper questions and so on, I've asked you for things like a 30% duty cycle or a 90% duty cycle to tell me what is the DC value of that. Okay? Get the DC value, after calculate C0, and then you do the substitution. What about the rest of the signal? What are the harmonics or the amplitudes of the first 3 harmonics, including the fundamental? So the fundamental will be omega 0. The next harmonic will be 2 omega 0. And the next harmonic will be 3 omega 0. So to do that, we go back to the synthesis equation that we had before. Right, the synthesis equation, and you now have to do a little bit of extra math in this case, because this now we have to do the integration. We know this is 1, so we're going to have to integrate now e to the minus jk omega 0 between minus t over 2 and t over 2. In this case, of course, it is going to be the actual value of xt goes between t1 and minus t1. And if you do that very carefully, right? And we'll leave that. This is part of one of the later problem sets that you will have. If you do that very carefully, you're going to get that CK is going to be something which is sine 2 pi k T1 over T. Remember, T1 over T has to do with it on the duty cycle over K pi. So C1 is 1 over pi. Everybody following so far, right? You understand what we're doing? I mean, this is kind of moving forward from what you would have covered already. Anybody not following?
So you could explain the limits if you got in for the second solution, the limits of CK.
Right. Okay. So CK is running, the formula for CK is supposed to integrate over the period of the signal. But if you look at XT, in as it is given, XT is 1. In this case, XT equal to 1 for T less than T1 or greater than minus T1. So, and 0 elsewhere, right? That particular part. And of course, the signal is periodic. So it will have what do you call it? XT plus capital T equal to 1 or 0, or XT plus capital T equal XT. You would have known that from what you did before. So if I integrating here, in fact, the integrals XT is only defined from T1 to minus T1. So I could change this limit here to T1 to minus T1 because in the rest it is 0. Yeah?
Yes, sir.
Right? So once you do that and you do the integration, and of course you're going to have to go backward and forward a little bit because you're going to get this in terms of E, and then you could substitute using Euler's formula relationships again. So you can get it now in terms of this sine 2 pi k T1 over K pi. If you substitute now for the 50% duty cycle, there's a relationship between T1 and T. Notice that is 2T1, right? So for the 50% duty cycle, 2T1 over T, which is that, is equal to a half. Because our 50% duty cycle, 50% is a half. So in other words, T is equal to 4T1. So if I substitute T equal to 4T1 here, right, which is what I'm saying here, you get that C1 is 1 over pi. Remember, pi is a number. Pi is 3.1416, and it's going down to, I forget, they reach a couple million decimal places, and it's still not repeating. So they're doing well. 1 over pi is about 1 over 3. When you substitute for k equal to 2, so k equal to 1 here is the first harmonic. K equal to 2, you get 0. K equal to 3, you get minus a third pi. Oh, sorry, 1 over 3 pi. If you were to continue, you would get C4 is 0. C5 is a very small positive number. C6 is 0, and so you keep going on. So this particular signal only has odd harmonics. And if you plot the harmonics for it, this is what the spectrum of that signal looks like, the first 3 signals, the first 3 components of it. So there's a DC, which is a half. Notice this is for the 50%. So the 50% duty cycle has a half. If this is 1 volt, then has a half volt DC component. It has something at the fundamental, which is 1 over, sorry, what was it, 1 over pi? All right. We don't have another one. We have minus 1 over 3 pi. And if you were to plot 4, you wouldn't have anything. 5, there's a very little one. 6 is nothing. 7 is a very little -1, and it gets down very low. So you can see now from this, if you were to, going back to some of this stuff that we spoke about, if I were to put a signal like this into a system, put this into some system here, put that in, what I am in effect doing is to tell the system, okay, it's almost like if I sat down and put a 1/2 volt DC on this and then see what happens, then put omega 0, you'll have to calculate omega 0 based on what, if you're given values for T, you sit down, you sit down with a signal generator and generate a signal of omega 0 and amplitude 1/pi and send it in. And then same time you send you send -1/3pi or 3 times that, and then whatever 5 omega is. So in other words, by putting this into a system, what you're doing is to impose a series of signals onto the system. Okay, but this is now telling us what exactly are those signals that we are putting in. Okay, so that is a spectrum of it, are the amplitudes inside of here. Okay, so everybody following conceptually is making sense? Some of this is revision, but some of it I'm going to slant a little bit differently as we go forward. Right? It makes sense. Yes, no, maybe. Good. A couple of people saying yes on the chat. So good. 3 people we well batted. What about this? If I were to drop this on you and tell you what are the first 3 harmonics of this? Right? So this is still a 50% duty cycle. Right? This is a little homework exercise that we'll do, and we'll take it up in a tutorial as a solution. But again, do you expect this to have the first 3 harmonics? Do you expect the first 3 harmonics of this to be different from that one if the duty cycle is the same? Should it be different or would it be the same? Think carefully. Same harmonics or different harmonics? Okay, one person is saying the same. Other people agree with that? Yeah or no? Conceptually or instinctively, should it be the same? If I didn't have, and to answer that, take away this axis here. If I gave you this just by itself and told you that was a 50% duty cycle, right? Square wave. The harmonics of that are fixed. Once it's a 50% duty cycle, the harmonics are fixed. So whether I look at it here, this is my time 0 when I start to look at it, or here, I am not going to change the harmonics of it. What I am changing is this sort of time relationship between where I look at it, where I start looking at it, and what the signal is actually doing at that point in time. So if I start looking at it here, the signal does nothing and then starts to change. If I start looking at it here, the signal is already 1 when I start looking at it and then it changes. Here, which is where we started, it's 1, but it changes after just about half the period of time and then goes back and does whatever it wants. So the only thing changing is my time relationship with the signal. In other words, the phase. So when you do this one, when you apply the complex Fourier series to this particular signal, you your intuition is telling you that C0, C1, C2, C3 going to be the same. They must. But because there is a time difference now, I'm looking at it differently. Before I was looking at it from here. Now I'm looking at it a little bit earlier. There's going to be something else appearing inside of here. And if you remember, that's something else in time, that shift in time in a signal is what we call a phase. So you're going to get the same amplitudes, but there's going to be a phase value inside of here. So it's kind of like you take a sinusoid, right? If you look at the sine, if this is a sinusoid by itself, if I start looking at the sinusoid at this point, sorry, at this point right here where it crosses u, right? This is sine omega t. If I started to look at the sinusoid here, this is cosine omega t, right? But you know that cosine is just sine omega t plus pi over 2. In other words, that phase angle has come in, right? If I looked at it here, that is minus cosine. So there's a sine plus a pi phase angle. So the same thing is going to happen here when you look at it. You're going to get the same components, but that phase is going to come in inside of there and play. And that is an important thing, that when you're dealing with signals, and you have the spectrum, the magnitude of the spectrum, right, which are the values of the C0s, is one part of the answer, but the phase is also the other part. It tells you the relationship between all of the components, and it makes a big deal in it. For instance, if you have two sinusoids, if I have two sinusoids of the same frequency, if I add them up in phase, I get one that is twice the amplitude. If I add them up totally out of phase, I get nothing. Yeah? So that phase is a very important characteristic of the components inside of here. So there are two things that will crop up, the magnitude part and the phase part. Okay? So everybody, at least you understand that. You're following what we're trying to do. Some of it is revision. Some of it is maybe a slightly different approach to it. What we're going to do in tomorrow's class now is to take this particular concept and move it forward now. We're dealing with periodic signals. What happens now if the signal is not periodic? And this is going to lead us to something called the Fourier transform. All right? So any questions? Could you state the topics coming for end of term, the whole course? Well, everything that we do. Oh, midterm. Midterm is going up to block diagrams. I think I mentioned that in class last time, or a little way back, right? So the cutoff for it will be up to block diagrams. I could ask you up to that, okay? Which is lecture what, 13? I think it was lecture 13 or 40, whichever was the last one where we did the simplification of block diagrams. All right. Okay. Any other concerns, questions? All right. Okay. So that's it for today, folks. Let me stop the recording and